Hi, everybody. My name's Lili. I'm from San Jose State University. I'm here with my colleague, it's Professor Sotoudeh, Hamedi-Hagh. We both from electrical engineering department. So, but I know here most people is from either computer science or computer engineering, probably. We are talking about the computing aspect of memories. So I think they have very strong connection with the computer industry. So that's my headline of my talk. First, I will give a brief introduction. So first, the demand in the memories. So for talk about actually, yesterday the keynote speaker, I think it's Facebook AI director, he mentioned several times about the demand in high performance, high quality memories. So this is more, I think, is to see the future of the development of the computer. Okay, so I listed something. Actually, semiconductor industry has long looking for the high quality, high density, high speed. As now, I think yesterday I also mentioned the high frequency or high bandwidth, the low power memory device that retains data even the power is interrupted. So this we call the non-volatile memory. So DRAM is we well know the dynamic random access memory used in today's computer. It must be continuously powered to keep its memory state. Right? That's specifically we use the most now for the DRAM. And they compare, for example, the flash memory, which is non-volatile, but it's much slower. In the ordinary work, we don't know, but in a computer, they need much more higher speed. And slow writing speed, and limited the number of write and erase cycles. So probably we know after many times use, then it will not work. Actually, sometimes you don't not many times use will not work. So traditional memory is rapidly approaching the minimization limit as the processing technology limitation. So this we all know, because when we make a memory, go with the MOSFET, right? Okay, the whole circuit with MOSFET. So the MOSFET itself is shrinking, so memories go with it. It's at the same time, so the processing technology for a long time we know is trying to hit the brick wall, but actually, thanks for the advancing of the processing technology. So now it's still, you go to nanoscale, still working. So this is why the memory also is go the nanoscale. So we talk about the nano-sized memories. Here, a little review of the universal memories. So the ferroelectronics memory is called FRAM, phase change memory, and I think now it's sometimes used together with, we talk about resistance change memory, just you use different materials. And two ones. And the magnetoresistive RAM. And then the last one we talk is resist change memory. Sorry, just type for the numbers. It's some book is, some places write called ReRAM, or some just called RRAM. Resist change memory is we talk about. That memory has a long time people has the theoretical model. Okay, but then the fabrication just I don't say recent years, still more than 10 years. Okay, but just not in practical market yet. The structure is basically is like a sandwich, the metal insulator, and the metal is like you use a capacitor, the situation. And for example, the platinum and the titanium oxide, dioxide, and the platinum, the structure. And we use two resistant status for the memory is high resistance state is called HRS, and the low resistance state is called LRS. And we have two basic switching behaviors because there's a lot of study to discuss the switching behavior. So unipolar and bipolar. So this is, I think, is published a while and widely used, cited everywhere. And the classification of the switching memory, the two major one, we use the bipolar and unipolar just mentioned. Okay, so it's just actually to show the different polarity when you have the bias polarity. So what about the memristor? In the title I mentioned what this work will talk about is memristor. Memristor, actually some people said the name talks were kind of weird. Memristors are resistance with memory, basically. Okay, so memories can store the data, and even when the power is turned off, that's what we need for non-volatile memory. And the earliest time is Leon Chua. He's the one invented, and he also gave the name of the memories. It's 1971. And that's Stan Williams, his team at HP lab. They fabricated the first memories successfully in 2008, and with speed only 1/10 of the normal DRAM. Okay. And, but later, of course, after him, there are many people did the work, and the universities to do the work. And they also move forward, but that's first when they fabricate. And the intended memories that I intended to use, of course, nano-electronic memory is for the size, and also computer logic, and among the others. Some important work, I just list some of this. Thus, I just mentioned 2008 is Stanley Williams, the team, published the first article is for the success fabricated. And then later, of course, there are more people and also more analysis. Actually, Leon Chua, he still is working in that work. He's doing many works in the circuit theory, and then this is one of them. And then some more newer, 2015 and 2018. Some is not a fabrication, it's just a theoretical analysis, gave the model, because still it's not very clear about the operation. So that's early the Leon Chua's model. And here we can see the most common, everybody knows, the three passive circuit element is resistor, capacitor, and the inductor. And they're related by charge, voltage, current, and then magnetic flux. Okay, and now Leon Chua, his model is 1971, his publication is mentioned there's a missing element. So that's the fourth one. His paper is seeking for the missing fourth element, and it's memristor. He named that M, so it's like we have resistance, capacitance, and inductance, then here memoritance, okay, as a quantitative describer. So this make the complete this like cubic for the fourth memories, the fourth one. So, but that's a long time. Since 1971, there's a lot of discussion. It's just based on the theory, but not really fabricated. It's very hard to do. But later, since the fabrication technology, and also somebody is really interested to do that work. So this is why Stanley Williams' team did that. But it's opened the path, like they paved the path for many people to continue the work. So our approach is just in our university, we did some work. So it's basically by our computer simulation analysis. So we did two basic work. One is we used a simulation to study the conduction mechanism, and the simulation memories is based on the Verilog model. And the Verilog model, the result, we did have the result to predicting the behavior of the memristor. Okay, as we expected, we get the result. And the second work is more recent, it's a Crossbar. Actually, many other place they did a crossbar structure model, and even to do the fabrication. But we only did the computer analysis, but we did some more detailed analysis by Matlab and Simulink programming. And that is basically we explore the various dimensions for crossbar structure impact on the behavior of the memories in the memory. And this work is more detailed in today's poster, okay, because this work is more recent. So we give a little model of the Verilog. It's the first work. So this is exactly follow the Leon Charles model. You can see that's an M defined as a quantity memory terms. It's like resistance, capacitance, those. And the W is just upside down because you want when you study for the voltage controlled memories, so you introduce a new term called the W, but it's not really new, just opposite, upside down of the M. So that's by simulation, you use the window function you have to use. So by some definition, and then of course it follows some other people's work to do further analysis. And this by simulation shows the frequency response. Here's higher frequency at 10 megahertz. It's not that high, but it did show the difference. You see the memories is deviated from the resistance. But if you go to a lower, the higher frequency, 1 gigahertz, and this actually it will become like a resistor, the memory resistor. They are redundancy together. The other one is lower frequency. And the first crossbar simulation, we use a mathematical model like that. I think it's harder to see the detail. In the poster, we probably mentioned it, and also the references more in there. And the method we used to show is the charge access is the input charge to the composite device, and it does not represent the charge of the individual memories. Of course, memories is still different with the device. So the charge of individual memories corresponding to the flux is obtained by adding its corresponding initial charge to the horizontal axis, which is this is hysteresis to show the loop, you see. But it is frequency dependent. You can see when the frequency go infinity, like we see go higher frequency, it becomes straight line. This is like same as it's become a resistor, right? It's not a resistor. But you can see the change because why we say it's resistance change of memory, because you see the axis is voltage and in the y-axis, and in the x-axis is current. So the ratio is the resistor, y divide the current, right, is resistor. So if keep the change, the value is as a curve, then that means your resistance, actually your resistance change. If it's straight line, of course, as constant. So this is why it's called a resistance change. So this show one of the case of the simulation. And that is considered the ideal case. So the width and the separation of the bar with D to show the best result, should show the hysteresis loop. And so that's about our work. And the summary is actually based on actually the computer work people probably know more. You probably have urgent need for the various memory, and then so your urgent need for today's circuit. And memory state based on the ReRAM, it has great potential in the future application. Computer simulation is a great tool for the research for novel memories by a memrist, which have a lot of advantage in performance, behavior, prediction, and the conduction mechanism analysis, and the design optimization, and so on. So for the future work, we need to continue in the computer simulation and the analysis of the memories themselves, because even memories themselves, that's a lot of argument for the different theory or models for it. And until, of course, even fabricated, the people realize it's really, you can do it and in the circuit. And the computation in the various novel structure memories, design optimization, and in-memory implementation. And the last, we really want to do the fabrication and the characterization, which is that, of course, is essential for the continued success. Okay, that's the end of my talk. And here, thank you for your attention.